All right. Hey, everybody. Welcome back. Sorry. Yeah, for folks on the Zoom, there are no TAs monitoring the Q&A, so please just message on the chat. I'll try to take a look at it every now and then and do my best to answer all of your questions. Cool. So a few announcements for today. We have homework 11 due Friday, turn early for bonus point. Project 3 checkpoints optional. So this is the last project. And then entire project is due 2 weeks from this Friday. So this will be a project on classification, which is something we're going to go over today. And then my office hours are actually today. So I normally have them on Mondays. They're today, 4 to 6 p.m. FSM. So come by. I'll be just heading over there like right after lecture. So feel free to walk with me if you have any questions. But I'll try to make sure I can answer as many questions as possible because I know we've been a little bit short-staffed on the office hours. And we are going to be trying to get together some sort of office hours tomorrow as well. We'll announce the times on Ed once we have that together, but we're working with some of the tutors to get that going. So cool. Any questions before we begin? Okay. All right. Cool. So today we are talking about prediction, which is something we've already done, but it's going to be in a slightly different context. So first of all, let's just review what prediction is. So fundamentally, when you talk about prediction in like data science or statistics, it really just means that you're guessing the value of some attribute that you don't know, and you're guessing this based on incomplete information. And so one way of making predictions, which is somewhat reasonable, is to find other individuals who are like the individual that you're trying to predict on and whose outcomes you know. This is really important. So that third bullet point is like super important. So, if I'm trying to make a prediction for some new person, let me try to find other people that look similar to them and whose outcomes I know, and then use those outcomes as a basis for our prediction. So this is kind of what we did when we first introduced linear regression. We had that scatter plot of like the child heights and the parent heights. And we said, okay, one way we could try to predict the height of a new child is we can go find other people who have similar parent heights. And then based on the height they ended up having as an adult, we could use the parent heights, like the average height of those people or something, as a prediction, right? So just find people that are similar, look at their outcomes, and then based on that, make your prediction. So that's kind of the general way all prediction is going to work in data science. And then we talked about how we can use a regression line. And so all of that was in the context of predicting something numerical. So we were predicting things like the height of this person or like the percentage in this district that's voting for Clinton. Those are all numerical attributes. What today and Friday is going to be about is actually predicting categories, which is called classification. So big differences there. So again, if it's numerical prediction, then it's called regression. That's what we've been doing the last few weeks. And then this week, we're talking about classification. We're predicting something categorical. So we'll go through a few examples of this today. But this is super, super common, where we might actually want to predict categories rather than just a numerical value. And that's really the only difference. And some of the techniques we're going to use for that are going to look really similar. So let's go through an example. So one really common example of classification is predicting whether your emails are spam or not. So this is something that your email provider is already doing. So if you go look at your inbox, you'll see that you have most of your emails are kind of in your inbox. And then if you go to your spam folder, you'll have several emails that are in the spam folder. And so what your email provider is doing is that they're looking through the contents of your email, and then they're figuring out, or at least trying to guess, whether it's spam or not. And so it's very similar. Like they don't really know whether it's spam or not, but they're just trying to guess that based on maybe past emails that you flagged as spam, and just the entire world of everybody flagging spam and not flagging spam. That's kind of what they've used to build that prediction. And that's what they're doing. So I thought it'd be kind of interesting as just like a exercise to show you some of the emails I've received and see if you can predict whether they are spam or not. So you can just kind of like raise your hand if you think it's spam. So we'll just go through these one by one. All right, so this first one, do you think this is spam or not? No, most people think no. Okay, this one is not spam for me. How about this one? I wish it wasn't, but it is spam, unfortunately. I would have loved to consider this. How about this one? Not spam. All right, you guys are good. All right. Yeah, so this is actually real. this was like a former classmate of mine from grad school. We happened to like reconnect after several years, and I like had a product launch for my company. So she was like really excited. So this is actually real. All right, how about this one? Most people thinking it's spam. Well, it's kind of split evenly, right? This one's a little bit tough to tell. Like for me, this would be spam, but like if I was really into Michael Kors handbags, like maybe this wouldn't be spam. And I'm actually really excited about that deal because that's a pretty good deal. So, it just depends on the person. Maybe for some people, this might be spam, might not be. This was for me, but it might not be for other people. But in general, that you've just kind of done what we're going to try to do is, classify whether these things belong in one category or another. And so you don't have perfect information, but based on what you've seen in the past, based on emails that you've seen of your own, maybe you've checked the spam folder now and then just because it does get it wrong sometimes. You kind of have a sense for like what's going on and like what might be or what might not be spam. And so that's basically one example of classification. And we'll be talking about how we can build some of these models. One thing to maybe think about is, what do you think the input is for this type of a prediction? Like, is the input numerical? Is it categorical? What do you think? Yeah. Yeah, it's text. So if we had to like pick between sort of numerical and categorical, what does text usually go into? Categorical, right? So it's a bit weird to think of it as categorical because there's like infinitely many categories in that case. Like there's all kinds of text you could make, but that's like typically how I think about it. But yeah, text is really the input here. And we're using text to determine whether this thing belongs in one category or another. So that's an example of classification. And so the general approach we're going to be talking about is actually, this is all just called machine learning. So we'll introduce this a little bit. You don't have to actually know this definition, but I thought it's helpful to just explain it to you. So basically, it's a mathematical model that is calculated based on sample data. We will typically call this training data in the context of machine learning. And then you're making predictions or decisions without being explicitly programmed to perform the task. So that last part is kind of like a word salad, but basically you're saying that you're not explicitly programming it in a particular way with like explicit rules. You're kind of just looking at the data, looking at the correlations of things, and kind of letting the model figure it out. Now, there is some structure to this algorithm, and we'll go through some examples of that. But you'll see basically that this is a little bit different than explicitly saying something. So an explicit algorithm would be something where I say like, if this email has like 5 exclamation marks in a row, it's spam. That would be an explicit algorithm. A kind of more data-driven algorithm would be like, let's look at the data and see how often that actually correlates with being spam. And we might find that like maybe that is something that correlates really highly with something being spam. And so therefore that's what tends to be predicted as spam. So, those are kind of 2 different ways you could do it. But the approach where you kind of use your data to figure out what's actually happening, that's what we call machine learning. And so technically you could say that a linear regression is machine learning. It's like probably the simplest form of just like fitting a straight line through something, but that is an example. And in general, these algorithms apply to both numerical predictions and categorical predictions. So we have machine learning algorithms for like regression and also for classification. All right, so that's also important to keep in mind. We'll mainly be focusing on classification though. So any questions about that before we continue? Yeah. Yeah, so what's the difference between training data and testing data? We'll go over that at the end of lecture. But that's a really good question. Yep. Any other questions? All right. Cool. So a few more examples of classification that I wanted to show you with different input types. I'm pretty excited to share some of these with you because this is actually most of the work I do in my job and that I've done before this. So this is pretty personal to me, minus the email part. So of course we saw this example where you have text as input, the output was spam or not spam. Another really common input is images. And so this is really commonly done in, for example, autonomous driving. So you might have like a camera that's capturing the scene around you. What it's capturing is the thing on top, which is basically just a picture. And then from that picture, we're making predictions about what's in the scene. And so in this case, what's the input? What is an image? If you think about it at the fundamental level, an image is just a bunch of pixels. And each of those pixels has these different values of like red, green, and blue. So technically, you can think of an image as just a bunch of numbers. It's going to be like millions of numbers, but that's really all it is. And then what this machine learning algorithm has to do is it has to take in that input and then output these different categories. So in this case, what it's doing is it's saying like all of the pixels corresponding to this part of the image are equal to a car. That's why it's blue here. All these pixels are equal to a road, and so on. So this is an example of what it's doing. So this is a little bit more complicated of an output. It's not just outputting like one single thing for the entire input. It's actually outputting a bunch of things for every single pixel, right? So this is like a little bit more complicated, but you could imagine maybe like a simplified version of this where I build an algorithm that like takes in an image and then all it outputs is like, should I stop or should I go? That's it, right? So that could be a way to like simplify it. But this just gives you a sense of some examples of this. And so I've worked on this problem really closely. I was at Tesla before. I was working on autonomous driving. So one of the problems I worked on, which is kind of cool, is it was a combination of classification and regression in one output. So in this case, what you're seeing here is this is actually a screen capture from an actual Tesla vehicle. And so we would take the image in, and then we would output not only the classification of what category each object is, but also how far away it is. So this is the distance to the car. This is in meters. And so we're outputting two things here. And so this is really common too. So you can actually have algorithms that will have like multiple predictions. They're both doing like regression and classification. And so this is a really important problem because I need to know not just what type of car it is, but like how far away it is from me, how fast is it moving, right? So these are all really important things. And machine learning was really helpful here because we were able to do this just using cameras. So like traditionally, you would need some sort of like depth-based sensor, like a radar or something like that to figure out how far away an object is. We figured out a way to build a mathematical algorithm that could just take pixels and figure out pretty accurately how far away objects are. So that's an example of using images. And so, yeah, it's going to be really common that we do both things. For most examples for this class, we're just going to focus on like just doing classification, but you could have situations where you're doing both. Yeah. That's a really good question. How would you do this in real time? Our notebooks sometimes take a while to run. So yeah, and our notebooks aren't doing something this complicated, right? So there's only like certain amount of resources that have been given to our notebooks when they're running in the cloud, right? They're running on some computer, but it's probably not like totally maxing out all the resources there. In an actual car like this, you would have some like pretty beefy like graphics processors that are able to run through like all these pixels really, really quickly. And the other cool thing about video and image in general is like you can do things in parallel. So like all those pixels can be processed in parallel. So you might have an image that has like 1 million pixels, but they can be all spread out and like all the work can be spread out. So there's like a lot of parallelization you can do. And if you're playing video games, you're already doing this. So like any video game console is going to do this also. And that's why they're able to run at such high frame rates. But it's all very similar concepts. Yeah, it's a really good question. Yeah, any other questions about this example? Yeah. Yeah, the input's just the pixels. So like, imagine I have an image that's like, let's say I'm doing a video recording at like 1080p. And so what is a video? A video is just like several image frames per second. So, maybe you're recording at like 30 FPS. That means you have 30 images per second being captured. And then each image is, maybe 1920 pixels by 1080 pixels. So multiply that out. That's how many pixels you have. It's a lot. And so that's basically like how many pixels you have in the image. And that's actually the input. Each pixel is basically just like 3 numbers. It's like red, green, and blue. You can think of it like that. They're all numbers on a scale from 0 to 255 usually. And so essentially it's like 3 numbers times however many pixels you have. That's the input. It's massive. It's really big. But that's basically what's happening. It's just numbers at the end of the day. Yeah. Any other questions? Cool. All right, so one more example I want to show you, which is kind of cool. This is related to the work I'm doing right now. So I have a startup right now that's working in sports. And what we do is we take video as input and then we output categories. And we have to use video because like we're so focused on like ball sports. And so the balls are moving like really, really fast. And so you can't just do like 1 frame at a time. You actually have to like take a bunch of video as input. So to show you some examples of this, it's kind of cool. So on the left, we have like a basketball example. Here we have a tennis example, but they're both doing very similar things. So they're taking in video as input and then they're outputting like whether things are going in or out. So for example, in the basketball case, this is automatically telling us like whether they're actually scoring the ball or not. This is an actual app you can download on your phone. It's pretty cool. And so your phone now has the ability to process this video at very high frame rates. And it already has like all that graphics processing that you need, which is really cool. And then the tennis case, it's doing more than just telling you whether it's in or out. It's actually telling you like the speed of the ball. So this is kind of doing like a regression and a classification at the same time. But this is an interesting example of how you might need video as an input. So if you just looked at one frame at a time, you wouldn't really be able to figure out necessarily all the information. You need the context of the entire video. And so this is an example of that. And so as I just mentioned, a video is really the same thing as an image. You just have several times per second, many images coming in. And so you could have like a model that takes in like 10 frames at once and then outputs something based on those 10 frames. That'd be one way that you could process video. But processing is still similar. The output's still similar. Cool. Yeah, question? Is Swingvision hiring for summer 2023 interns? Yes, we are hiring. You can check out our website. Yes, good question. Any other questions? Yeah.
So for like the Swingvision drafting, does it do it? So it doesn't do it one frame at a time. Or like how will we process the algorithm on like 2 frames in a row?
Yeah, it's going to do a few frames in a row. It doesn't necessarily do like a lot of frames because there's also like memory constraints too. Like every image is pretty big. Like I think each image is probably going to be around like 5 megabytes. And so, you know, if you want to keep like all those frames at once, your phone will kind of max out in memory. So we try to do like a couple frames at a time. We pass that into the model and then it outputs things. And then it's what we're doing is, for example, if you're trying to predict whether something's in or out, you would have to do like several predictions probably, and then sort of like smooth it out or take an average or something. And then what's also kind of cool is you can build models where not only is the input like an image frame, it's also the output of the last result. So you can keep a sense of like memory. So that's also really common. And that's important for like the autonomous driving case as well. Like I need to have some context of like where things were in the previous timestamp. So yeah, you can build some really complex things. It gets very interesting. Yeah, good question. Yeah. You mean because it's 3D or? I mean, it's just basically like visually, if you can tell, right? So what you'd want to do is just get a bunch of examples. Like if we go back to actually the definition of how we're doing predictions, this third bullet point, right? Whose outcomes you know. So if you have past examples and then you know what their outcomes are, maybe just visually looking at it, then you can train this algorithm to make the same predictions. So that's really the key for all these algorithms. It's like you need to have examples of the data, but also what the actual outcome is. Like how far was that car in that specific case? We need to have lots of examples of that thing. So I can't just like magically figure it out. We do have to have examples. You have to label your data in some way. Yeah, that's a really good question too. Any other questions? Cool. All right, let's look at an actual example of data. So it's not going to be video, unfortunately, but it's still really cool. So this is going to be an example that's in medicine. This is actually, I feel like, the most underutilized domain for machine learning still. If you're interested in medicine or interested in machine learning, this is like a great field to go into because there just hasn't been that much yet. Starting to see more of it. And so in this case, we have several patients. So each row is a patient. And then we have all these properties that we observe about them. Some of you might be familiar with some of these columns. I certainly am not familiar with most of these. I guess I know potassium and sodium, but yeah. So you can kind of see all these different things that we're observing about them. And then finally at the end here, we have a class. So this class is like the category that we're going to try to predict. So we have a bunch of patients here whose category we know. What's going to happen is there's going to be some new patient that's going to come in, and we want to try to predict what their category is. And so the way that the category was determined in this case was that they had to go through a series of tests. So they had to go through several labs. Maybe they had to do like, some sort of like blood test, and just maybe that blood itself needed to be tested in like a bunch of different ways, very expensive process, and tested for all these different things. And then all these different attributes had to be determined for their kind of blood, let's say. And then from that, some expert would have to kind of go through this and be like, okay, based on everything that we're seeing here, the combination of all these values, we feel that they have this condition. In this case, this is chronic kidney disease. So maybe like a nephrologist needs to look at like all these results and be like, yes, they have it, or no, they don't, right? And so this whole process like takes a really long time, and it's very expensive. And so it would be nice if maybe we didn't have to make these tests so complicated. Like maybe we could just do a test and just look for like 2 of these columns, get those values, and then make a prediction just based on 2 columns. Like maybe that would actually work out decently well. Maybe there's a way to do that. And so that's what we're going to try to do. And if we can actually achieve this, then we could save like patients a lot of money. Just the entire healthcare system could be a lot more efficient, right? We wouldn't have to necessarily go through all these tests, or maybe we wouldn't like fully solve the problem, but we get to a point where we could drastically reduce the number of people who need to go through all the tests, right? Like we might be able to flag a bunch of people like, you guys are okay, you don't need to go through the rest of these tests, and we just saved you a bunch of money and time, right? So those are some advantages of trying to do it more simply. And so that's what we're going to try to do here. So firstly, let's take a look at how many people are in each category. And so here we have 115 people in the 0 class, 43 in the 1. So typically when you're looking with medical data, we'll usually use 1 to represent like having the condition, like being positive for this thing. So in this case, that's how many people have chronic kidney disease in this data set, and then 115 don't. And so one thing we can try, for example, is let's look at white blood cell count and glucose. So just try 2 things, and let's see what we get. So in this case, what we're going to see is kind of a new visualization. This is going to be a scatter plot of white blood cell count and glucose, but we're also visualizing a 3rd variable, which is the category, and that's being designated by the color of the scatter plot. So this is kind of the usual scatter plot we're used to seeing, but we're just visualizing a 3rd dimension, basically, which is what category they're in. And so you can see here, these are the people that are category 1, class of 1, and then this is the class of 0. And so any interesting like patterns that jump out to you when you look at this? What do you notice? Yeah. Yeah, so towards the left side, it looks like we have like blue and gold both kind of overlapping a little bit there, right? So that's kind of interesting. So there isn't really like a clear separation necessarily. Anything else that kind of jumps out? Yeah. Yeah, so there's clear separation if you're outside of this little region here, right? So like if we're outside of this corner, we pretty confident it's a 1. Whereas if you're inside, like you might be 1, you might not be 1. So it's kind of interesting. So it almost makes it seem like this range here is maybe like healthy levels of these counts. But then as you start to get out of these healthy levels, it's like a pretty good chance that there's something wrong. But then you could still have healthy levels and like still have this condition. Maybe there's like something else that's messed up with the kidneys, right? So like that's something interesting that you can see there. So there's like one direction where we can make like pretty good predictions, but like other parts of the scatter plot, it's going to be a little bit harder. Cool. Let's try another 2. So let's try hemoglobin and glucose. So in this case, we see something like this. So any thoughts on this one? What do you see here? Yeah. Yeah, there's more clear separation, right, between these 2. So I see like all the blue dots are over here in the bottom right, and then pretty much all the gold dots are out in the left or above. And then even if we zoom in, like there isn't really any gold happening here. These 2 are like kind of close, but other than that, for the most part, it looks like you can kind of see the separation pretty quickly. So a question for you, if I put my cursor like over here at 12.5 and 200, what would you, let's say this is a new person that comes in, what would you predict for them? Would you do 1 or 0? You can do it with your hands. Okay. Yeah, so most people are saying 1, right? How about if I'm like over here, like in the middle of this square rectangle? 1, 0, not sure. Yeah, this is a tough one, right? Because like it certainly seems closer to this blob of blue points, but it is still like pretty far from like this boundary that it seems like there's like a little edge here once you go beyond that, right? So I don't know if we're like in the danger zone, like what's going on, right? So it's kind of tough, hard to say. Maybe we don't have enough data. This is just a sample of people after all. Maybe we need to see the entire population to actually tell, right? But one way to think about it is like in the population, there is some kind of clear difference between these 2. Like there is some part where I should be switching the prediction from blue to gold, but we can't really observe that because we are only seeing a sample of individuals. And so we have to just see like what's the best we could do with this sample of individuals. So yeah, but you guys are building the right intuition, which is great. So let's try to build a explicit model to predict whether a new person is in the 0 or 1 class, right? So we're going to try to do this by just looking at this, just eyeballing it. So I think what we're going to basically notice is that it looks like if I'm kind of above, if I draw some imaginary line over here, if I'm above the line, I'm going to be a 1, or if I'm to the left of like some line over here, I'm also going to be a 1. So maybe that's one way I could make a rule. And I'm just going to make that arbitrarily. I don't know if it's actually like going to work in the population, but it certainly seems like it's going to work here. So we could go ahead and try that. So what we can do is we can try to figure out what's kind of like the maximum glucose value to be in this region. That's what this first line is going to do. And then what's the minimum hemoglobin value on the left side of this cluster of points. So that's what both of these are going to do. So for the maximum glucose, what we're going to say is, let's take everybody whose class is equal to 0, look at the glucose column, and then find the maximum. So that's basically saying take all the blue points, find the maximum value. And then the bottom one is saying take everybody who's 0, and then look at the minimum hemoglobin. So take all the blue points, find the smallest hemoglobin value. So now we have like our limits. So just go ahead and run this. And then if we wanted to actually make a classifier, this is again a very explicit classifier, but it is a classifier nonetheless. We could just put it in as the rules that we just said. So if hemoglobin is below that minimum value or the glucose is above that maximum value, then we're going to return 1. You have this condition. Otherwise, we return 0. And so we can go ahead and run this, and then we can try it out. So for example, we could try 15,100. So 15,100 would be right here. So we'd expect this to be blue. And so we could try this out, and we get 0 as expected. And then we could do 10,300. So that's going to be all the way up here. So it's like very much inside the gold area. And we get a prediction of 1 in this case. All right. So this is like one way to build a classifier. I mean, we were pretty explicit about this. We kind of just eyeballed this, and it seems to work like it's going to work pretty well for this data set, but we don't really know if this is actually going to work well for the entire population. So we need to do something a little more sophisticated. But that just gives you a sense of like how you could make an explicit classifier. Towards the end of the lecture, we'll talk about how we can actually make a more data-driven classifier. Any questions about that example? Yeah. Yeah, what we did for the max and the min, all we did was we just found out what's the maximum sort of height inside the blue area, and then what's the minimum like on the x-axis in the blue area. So minimum hemoglobin is like what's the leftmost thing, and then what's the tallest part. That's what we did for the limits. Yeah. Oh, would you want to do and, or do you want to do or? So because we're doing it for the yellow case actually you can just do it with or. If you were to flip this and do it based with like an and statement, then you would need to, you'd probably put this stuff over here, and then you'd have to do like an and. Yeah, so it depends on which one you're doing, but both work, yeah. Yeah. Yeah, so right now we're running the classifier on existing values. Well, actually, technically this isn't an existing value. We just made this up. But we built the classifier using a sample of data, right? That's how we came up with these limits. We like took a sample of people, we saw something interesting, we like made the classifier based on them, but now we would go and apply it to new people. That's how you'd want to use it. And then one thing you want to do before you apply it to new individuals is you want to test out what the accuracy is. And so one way you can do that is you can run it on your existing sample. That's one way that you could test it. Yeah, good questions. Any other questions? Yeah.
Why do we dislike explicit models?
Oh, why do we dislike explicit models? That's a really good question. So, I mean, in this case, like we just happen to get this sample of data, right? And like, it might be the case that like this region is also totally safe, and maybe for some reason, like the sampling was just done incorrectly or whatever. You know, and sometimes it'll be more nuanced than that. But that's basically the thing. Like you want to actually make sure that your model will perform well for like a diverse set of people, and it's not like too specific to the individuals that you happen to sample. And so that's why doing a more like correlation-based approach is going to typically be like more robust to diverse data sets. Yeah. You could think of it similarly in like the linear regression case too, right? Like if I was just looking at a scatter plot and I just kind of draw a line that like looks good to me, like it may not be totally right. When you actually go through the regression model, it takes into account like all of the data that's there and then like averages things out, right? That's kind of what you'd want to do in this case. Like in this case, we're just kind of paying attention to like the things on the boundary. We're not considering all this stuff out here when we made that decision, right? Maybe we want to use those things to like pull it out a little bit or something like that. So that's kind of how we'll try to do it later in the demo. Cool. Yeah, really good questions. Cool. Let's do another example. This one's a little bit interesting. So this is going to be about classifying banknotes, which are basically just like, think of them like bills. Think of this as just like dollar bills. and you're trying to classify whether it's like fake or real. And so in this case, we have a bunch of variables. Again, here, we don't really know what these things mean, just like the last case, unless you're like a biology expert. You probably didn't know what a lot of those things meant, and that's okay. It's the same thing here. So what's happened here is some like fraud expert has taken these notes and like analyzed them, found some way to like simplify it. And based on that, they are then coming up with these properties that they think are important in predicting whether something is fraud or not. And so they've come up with these different variables. We have our class here once again. And so we're going to try to go through the same exercise of like visualizing pairs of these and like see if you notice anything interesting in terms of patterns. So first of all, always good to just get a sense of like how much data you have. So this one's a little bit more balanced, which is interesting. So we have several that are kind of fraudulent and then most that are not, but it's almost 50-50. And so we can just try like a couple of variables here and see what happens. So we see some like interesting pattern like this. And so we've tried these two variables and we see basically that there's like quite a bit of overlap in the middle here. Yeah, any other interesting, I guess, patterns that you notice here? Would you want to use this, do you think, to make predictions? Like, do you feel like this is going to work well? Not really. Maybe. I mean, it's going to work well like a lot of the time, right? Like if you're in this part of the scatter plot, it's going to work really well. If you're up here, it's going to work really well. It seems like once we get over here, it's going to be kind of tough, right? So it kind of depends on what you care about. But like in general, it's looking like a decent chunk it's not going to work that well. We can try another couple. So let's try these. So you get some weird shape like this. Kind of interesting that they both have like similar shapes, but they're just like a little bit off from each other, right? And so this is actually going to be really common. In fact, this is going to be more of what you're going to see most of the time. So in an actual data science problem, it's going to be really common that like your data sets, your scatter plots in this kind of a view, when you're just visualizing two variables, are going to overlap a lot. And so we talked about separation. It's typically going to be really hard to find like a really clear separation between both of the categories. And so sometimes that means that, well, we just can't really do that much better. Maybe we need to go find some other properties that might be more interesting and might have a better separation. Like maybe we're not getting that much interesting information out of these properties. That's one thing that it could mean. But another thing it could mean is that we are simplifying the problem too much. And so we talked about this actually at the very first lecture, which is like when you have this data set, it's basically this like cloud of information, and we take snapshots of that information. When you visualize your data set, which has all these different properties, when you just look at two of them, you are simplifying the picture, right? You're basically like taking a subset of your information. So that's what we've done here. The actual picture could be a lot more interesting, but we're just looking at this from like a particular angle of just these two variables. So let's see what happens if we actually try to visualize 3 numerical variables and see there's a separation when you look at 3 variables. So this is the first time we've done this in the course. So let's take a look at this. It's kind of cool. So we're going to visualize in 3 dimensions. Are you ready? All right, check that out. Cool, right? So this is what we see in 3 dimensions. So now here we have one variable on this axis, another variable on this axis, and then yet another going up. And so now we start to see like, actually there is some sort of a separation here, which is kind of interesting. And so maybe now if a new point came in, we'd be able to like see which cluster of points it's closer to. And then based on that, we can actually make a pretty good prediction most of the time, it looks like. There's still going to be some overlap, it looks like over here, but in general, there is like a much better separation than we were seeing before. And one way I like to think about this is like, you can just imagine, if I put my fist like this, from your perspective, it looks like they're on top of each other, right? But if I look at it from a different angle, they're not. There's actually separation there. That's essentially what's happening here. So you have all your data points, and they are actually kind of looking like they're overlapping depending on what angle you look at the data. But if you're actually able to add a 3rd dimension, it lets you see that there is actually a separation there. And so for this data set, it's pretty interesting because like, if I were, for example, standing over here and looking straight on like this, if you're standing over here, that's very similar to like the plot we saw above, where you're kind of seeing it from one side, right? And so it's like, I can't tell if there's a gap here. But when you see it in 3 dimensions, you can. And so this is going to be super common that in lower dimensions, we can't actually see the separation. And sometimes you have to go to 3 dimensions. Sometimes you might have to go to more than 3 dimensions, actually. And we will do that in the next lecture. And so in that case, what would we do? We can't really visualize more than 3 dimensions, unfortunately. It's really hard to even process like what that means. So what we're going to have to do basically is just come up with a way to determine how far apart 2 things are in that dimension. So, as long as you have a way to figure out that like a new point comes in over here and it's closer to the purple area than the yellow area, as long as I have a way to figure out like how close something is to our existing data set, that's all you need to be able to do. If you can just do that mathematically, then you don't need to worry about actually visualizing it, right? And so that's what we're going to be doing. So we're going to figure out a way to like figure out how close something is to our sample data. And then based on that, we will then make predictions. And it's okay if we can't visualize. But this at least hopefully builds some intuition for like why we need to go to higher dimensions and why your predictions aren't working that well when you're just using like 2 variables. Cool. So any questions about this example? Yeah.
I noticed that whenever we're using something that we want to predict, we still have the same variables as what we create the model, right?
Yes, that's right.
But what if the variable produces something that needs to be tested in the lab, right? Just what your results know.
Yeah, so that's a good question. We do need to ultimately have the ability to observe the variables that are going to be the input to our model. And so if you go back to like the kidney example, here we observed like a lot of things, right? But we found, for example, in this case that like just using glucose and hemoglobin, we were able to make pretty good predictions, right? And so this could be a case where like your test is simplified quite a bit now. You just need to observe these 2 things. So like I still need to do some labs, but I don't need to make it as complex. Like this is a lot more complex, right? Like seeing all these things. So that's like where the advantage comes in, is like, can we simplify how much information we're using? You're probably still going to have to do some sort of, work, but it at least makes it more efficient is the idea. Yeah. Good question though. Yeah. Yeah, so what does it mean for them to be separated in 3 dimensions, but like still be overlapping in 2 dimensions? Yeah, I mean, it's just a matter of like perspective. So if I'm using just like these 2 variables to determine how far away something is, then I get into these issues where they're actually overlapping. But if you go into higher dimensions, you actually have that these are actually very different points. Like these 2 are different points on this graph. But on this graph, they might be like exactly the same point, but that's okay. It's just a matter of like perspective. You're going to have to use like more computation potentially to do it in higher dimensions, but that's okay. But they are actually different, even though they're the same points. It's just a matter of like, where are you looking at the data from? Yeah. Cool. Any other questions? All right. Cool. So let's talk about how we will actually solve some of these problems with a more data-driven approach. So what we're going to end up creating are these things called classifiers. Classifier is really just a model that's going to do classification. So in regression, technically you could call them regressors if you wanted to. No, it's not really a common term, but it's basically the same thing. It's just like whatever mathematical model you're choosing to make a classification. We technically built one already, but it was explicitly programmed. And so here's how we will do it non-explicitly. And so what we're going to do is we're going to train this classifier. So when you call it training, or essentially meaning is like, we're just going to ingest like all the data in our sample, look at the correlations, and then based on that, make predictions. And so the way this classifier works just off the bat is we're going to take these attributes of an example that we can observe that's going to be passed in as input to this classifier. It's going to do some math and then output a predicted label or category for this example. And so ideally, we'd want to build this classifier using the entire population. But if we had access to entire population data and all of their predicted values, then like we wouldn't need to build a classifier in the first place. So like typically what's going to actually happen is you have a sample of data, and then you're going to try to use that data to make your predictions. And then it's really important that not only do we have all these observed attributes, but we also have the labels. The label is the same thing as class. So I need to know the category of all these people, and I need to have all the other attributes of them. And then when I go out to get a new person, all I need is just the categories, or sorry, the attributes. And we're gonna try to make a prediction of the category from that. But this sample part is like, you want this to be the same between your data set and what you're making your prediction on. And so typically what we'll actually do is we'll split our sample into 2 pieces. And the reason we do this is because we were just talking about earlier, we want to get a sense for how accurate this algorithm is actually going to be. And so typically what we'll do is we'll build the algorithm using our training set. Once we've built it, we'll go ahead and run it on the test set and evaluate what the accuracy is. So for example, in the case where we were doing like hemoglobin and glucose, we could maybe take a subset of the data, look at its scatter plot, come up with a rule, and then try that rule on the other subset of the data. So like kind of split the scatter plot into two sets of data, create your rule based on one, and then go and run it on the other one and see how often it's correct. That's one way that you could sort of estimate the accuracy on the population. And this works because if I have a sample and I just randomly split it into like two groups, then each of those samples is a representative sample of the population. And so therefore, I can try to make this model based on my training data. It might have some bias, but then I have this other sample now, which actually is reflective of the population, and it's not necessarily related to the training data. I can go ahead and apply it on the test set. And then from that, I can come up with a sense of like how accurate this is actually going to be. Like maybe this thing categorizes things accurately like 95% of the time. And so based on that, I could say like, we feel pretty confident this is going to work well in the population. So that's going to be kind of the general flow of how we do things when we're building classifiers. And then this same approach could technically also apply to linear regression. So you could take like the scatter plots of that we've been looking at over the last few weeks and like split them up into two data sets, fit a line through one of them, then use the line to make predictions on your other data set. You could do that and evaluate like what's the MSE on the other data set or something. So like you could do that in that case as well. That's totally fine. But this is just a common thing that we're going to do in machine learning. It's a good way to evaluate your models. Yeah. Oh yeah, how much should the training set be relative to test set? It's really going to vary by problem. I would say in general, your training set's usually a lot larger because you want to get all of the edge cases and like rare examples. That's just really, really important. So especially as these problems get really complex, there's just lots of like edge cases and it's hard to find them. And so you want to include them in the training set. But yeah, oftentimes your training set will be larger, but there's no like necessarily clear-cut rule on how to split it. Like a good way to start is just like 50-50 if you want. If you have a large enough sample size on both, you could just do that. Yeah. Any other questions? All right. Cool. So yeah, this is just recapping what we just said. But basically, training sets what's used to build the model, test sets was used to estimate the accuracy of the classifier. Sweet. So this is generally how we're going to be building classifiers when we're trying to make a prediction about a category. And then we're going to use a very specific classifier, which is the nearest neighbor classifier. So this is just one version of it. Just like when we did regression, the very first thing we tried was we said, let's just put these intervals around, an individual and calculate the average height of everybody who's like in some small interval. That's how we did the initial prediction. And then we did that throughout the whole graph. And you saw this kind of like bumpy line, but it looks like a line. That's basically what we're going to do here. So we're going to say, new person comes in on the scatter plot. Let's look at a neighbor of people around them and then find the average output value or something, or the most common output value. And like, that's how we make our prediction. So that's what we're going to do. That's called a nearest neighbor classifier. And so the way it works is very similar. You take in your attributes that you're observing. Now what you do is specifically, you're going to find the most similar training example in the data sets. And then whatever their output is, that's what you're going to use as your prediction. So in this case, we're just using like one neighbor. But we'll see an example on Friday where you could change the number of neighbors to consider. Like instead of just looking at the single closest person on the scatter plot, we could look at like the 5 closest and see what's the most common value. So just to give you a sense of like how that would look visually, in this kind of example, basically like it's kind of what we were already doing, but it's a little bit more explicit. So if I have a point over here, I'd look through all of my points and find the single closest one. So the single closest one to this one would probably be this point right here. And so because that one's gold, I'm going to predict gold for this point over here as well. So that's basically how the algorithm is going to work. And so that's one way of making something that's not necessarily explicitly coded, and it just happens to depend on the shape of your data. And then we'll go through the same process the rest of the way through. So, we'll create a training set with the attributes, we have our outputs, and then we'll actually build this classifier based on just the examples in the training set. So like find the nearest neighbor in the training set, and that's how we make our prediction. But you can go ahead and still apply that to the test set without any issues. Yeah. Yeah. Yeah, so the question is basically what happens when you get to a situation where like kind of have like two neighbors that are like of opposite classes and they're both like equally close, right? So one way we try to get around this is like we'll typically use like a larger number of neighbors. Like don't just look at the single closest, look at like several, like maybe 9 or 11 or something like that. And so then it's very rare that you'll run into that situation. And then also if you're using like an odd number, you'll usually find there's like a majority class too. So it's pretty rare that you'll have like kind of 9 that are equally close on this side and 9 that are equally close on that side. Like the chance of that's going to get really low. So those are some ways you can get around it. If you really truly get to that kind of a point, it's almost like you should just flip a coin. Or I mean, if it's something more sensitive like medical data, you don't want to flip a coin on that. So you probably just say, let's just do some more tests. Like we're gonna err on the side of caution and be like, let's assume you might still have it. So let's go do some more tests. That's probably what you would do. Yeah.
Do we need to normalize the axes for the distances?
Yeah, that's a good question. Do you need to normalize the axes for the distances? Yes, you do. So these axes are on very different scales, right? So I have glucose here, which is going from like 0 to 500, and then hemoglobin is like only, you know, in like single, like low double digits. And so that can affect the distance calculations, right? Because like if I zoom into this here, if I have a point here, right? If I'm looking at like horizontal distance, it's very small to this point, but then like the vertical distance to that point, it looks roughly the same on the graph, but it's a lot more because of the units on the y-axis are like so large, right? So if you were to just look at like differences of like y values here to calculate a distance, you're going to get something very different when you compare vertical to horizontal. So standardization is really common. So yeah, it's going to be a common thing that we're going to put all of our data into standard units, then compute how far away things are, because you don't want to like inflate in a particular direction on the graph. Yeah, so that's a really good question too. Cool, so let's see some quick examples. I guess we don't have that much time of how we could do this. So we're just going to take our data, we're going to convert into standard units, and then we're going to just make a scatter plot of our information. And so here's how the nearest neighbor would work. So if I have a scatter plot, let's say this is a new point that comes in, all we do is like find the closest point, and that's a prediction. And we can change this around to see what would happen. So like it could lower this down farther on the graph. So I could make this like a 1 instead. Now it goes to this point. We can go a little bit further down further. Now it goes to this point. And see, that's basically how the single nearest neighbor would work. And then in principle, you could consider more than just the single nearest neighbor, which is what we're going to do on Friday, but that's kind of how it works. And then what's going to be interesting is as these points move around, we'll see that there's a certain point where the prediction changes. So like when we were at 1, the prediction was gold, but then when we move down just a little bit, let's try like 0.95. Now it becomes blue. So there's a certain point where it kind of flips on the other side. And so notice how this is flipping at 1, which is like quite a bit above here. Whereas before we made our explicit rule, it was like just outside of this, right? And so this is a case where it's a little bit more data driven, and you're kind of taking into account sort of the context of the entire scatter plot. You're not just taking account into like what we saw and felt like would make the most sense. And then if you just want to make that jump like more smooth, then we could consider more neighbors. And so one kind of cool way to visualize this is to actually look at a grid of all the possible points that we might want to predict on. And then we can actually go ahead and predict on every single one of these red points and then see what happens, which is kind of cool. You can actually just see like where it would actually flip. And so that point where it flips is called the decision boundary. And so here's what this looks like. So what this is saying is in all the points over here, you'd be predicting blue, and all the points over here, you'd be predicting yellow or gold, I should say. And then at this point, it flips over. And so you can see how this actually looks. So this is like a more data-driven separation compared to what we were doing before, which is kind of interesting. And so what we'll talk about on Friday is that this is what the separation looks like if you just consider the single closest neighbor, but this might look quite different if you consider a larger set of neighbors. So that's what we'll do on Friday. Cool. All right, we'll stop there. Thank you.